In this video, we are going to discuss about transfer function parameters. This is our second topic in our control systems. So here, as an introductory topic, we are going to discuss block diagrams. In this topic, we are going to discuss about some block diagrams and block diagram reductions, as well as signal flow graphs. So here in this class, we are going to define block diagrams or what block diagrams are. So as we start, block diagrams generally, as in control systems, contains a number of components. So the function of each component can be represented with a diagram. And so the diagrams are called block diagrams. So to define a block diagram is nothing but a pictorial representation of components integrated. So a block diagram is a pictorial representation of the control system showing a relationship between the input and the output. A pictorial representation of a control system showing the relationship between the input and the output. So this is what I'm saying. An input and an output. It has an input and it has an output. We have the input and the output. So this is just a pictorial representation of what a component is or what a control system is. It contains an input and an output. And here, this is a block diagram of a physical system. For example, a physical system can be a motor. It can be an electric iron, an electric kettle. That is just an example of a system. So we are going to see how some parts of the physical systems can be represented in block diagrams, So moving on to the next, we have some block diagram definitions. So the first one is the output. The output is the value of the input, which is multiplied with the value of the block gain to get the output. Multiplied by the value of the block gain to get the output. The next one, we have, so this is the input. We have the input and then we have the output. The input is represented by letter R and the output represented by letter C. So to find the output, we have said the value of the input is multiplied by the value of the block gain to get the input. The value of the block gain to get the output. The value of the input multiplied by the gain. The gain here is presented by letter G, or no, and by the input. You multiply the input and the gain to get the output. So moving on to the next definition. We have the input. So here we go. We have the summing point. The summing point is more than one signal. The summing point is more than one signal, which can be added or subtracted at the summing point. We have the summing point. The summing point is more than one signal that can be added or subtracted at the summing point. For example, here we have the input as X, and we have two inputs. We have input X and input Y. We have input X and input Y. So we have input X, and input Y. In here, we have an addition and a subtraction. So the first output can be Z, which will be equal to X plus Y. So we have added input X and input Y, or we can have Z equal to X minus Y. So we have subtracted input X and input Y. So a summing point is more than one signal. We have two signals. We have signal X and signal Y, or input X and input Y as input signals. They can be added or subtracted at the summing point. They can be added or subtracted at the summing point. So we move on to the next definition. The next definition, we have the takeoff point. We have the takeoff point. We have the takeoff point. So on the takeoff point, this is a point at which the output is taken for feedback purpose. The point at which the output is taken as feedback or for feedback purpose. So this is the takeoff point here. And we said our output is denoted as C. C means our output in this case. C is our output. And then this dotted part here, the dotted part is the takeoff point. So this takeoff point, this is a point at which the output here is taken for feedback. This one shows, the arrow shows feedback. The arrow shows the feedback. Arrow shows feedback. Arrow shows the feedback. Moving on to our next definition, we have a canonical form. A canonical form, this is a diagram or a diagram, yes, of a block that shows the simplest form of a feedback control system. We said we can have control systems, or we can have physical systems such as electric kettles, motors, iron, the electric iron, we can have a firing gun. So we can have those systems represented using blocks, So a canonical form of a block diagram, consists of one forward path. This is a forward path. A forward path starts from the input to the output. A forward path starts from the input to the output. That is a forward path. And then the canonical form consists of one feedback path. One feedback path starts from the input to the output. One feedback path starts from the output to the input. That is only one, because we only have one block, or we have one block, which is the feedback path. And then it contains one summing point. It has one summing point. This is the symbol of a summing point. And then it has one takeoff point. This is our takeoff point here, a takeoff point. So we have a control system of a canonical form, of a block diagram, consists of one forward path, one feedback path, one summing point, and one takeoff point. We have said the forward path starts from the input to the output, whereas the feedback path starts from the output to the input. And then we have a summing point. And a takeoff point, So moving on to the next. So we have the transfer function, which was our discussion today in our class, transfer function. So how do we represent transfer functions of different diagrams? How do we find transfer functions of different control systems? By definition, a transfer function is the ratio. Of the output signal, So transfer function, you can write the short form of a transfer function as TF to show that the ratio of the output signal, to the ratio of the input signal, So for example, in our diagram, we had the output as C, denoted by C, and our input denoted by R, subscript S. So S represents the Laplace transform of the T. S is the Laplace transform of T, which is S is the frequency domain, while T is the T domain or time domain. So S is the Laplace transform of T. T is the time domain, while S is the frequency domain. So here we have R, as you have already said, we have R of S. S is the Laplace transform of T. And small r, we have small r here, as you can see, and we have capital R. So R, to get the Laplace transform, it becomes R, capital R. C was our output, which is the controlled output. small c becomes capital C, which is the Laplace transform. And then we have the error signal, the Laplace transform of small e of the error signal becomes capital E, whereby we have the feedback signal, that is the feedback signal. And then we have the forward transfer function. G represents the forward transfer function, while H represents the feedback transfer function. Those are the Laplace transforms of the different these are the Laplace transforms of these. We have small add the input. C, we have the control E, we have the control output. E represents the error signal, while B represents the feedback signal or the primary feedback signal. G is our forward transfer function, and H is our feedback transfer function, Moving on to the next point, we have control ratio. We have the control ratio. The control ratio is the same as the closed loop transfer function, which we have already said that the control ratio here we have said that is the ratio of the output to the input. This is our closed loop transfer function or the control ratio. And then we have the error ratio. Error ratio is the ratio of the error to input. Then finding the Laplace transform. We have that as our error ratio. That is our error ratio or the actuating signal ratio. And then finally, we have the primary feedback ratio. The primary feedback ratio, this is the ratio of the primary feedback signal, to the ratio of the input, of the input. Now finding the Laplace transform, we have that. This is our Laplace transform. The Laplace transform of the primary feedback ratio. Now this is our feedback ratio. The feedback ratio is the ratio between the ratio of primary feedback signal or the feedback signal to the input. Those are some of our definitions that we are going to see forward when we derive some transfer functions. So we have different transfer. We have the closed loop transfer function, the primary feedback ratio, and the error ratio. That is what we are going to derive. In our. So when we have some. So this is what we are going to derive. You have an let's draw. We want to derive the control ratio, the error ratio, and the primary feedback ratio in our next class. So far we have learned some. We have the block diagrams. We have different block diagrams. So when we started, we defined the block diagram as a pictorial presentation of the control system, showing the relationship between the input and the output. So we have the input and we have the output. So the output is the value. Output is the value of the input multiplied with the value of the block gain to get the output, multiplied by the value of the gain to get the output. Then we had the summing point. The summing point is more than one signal that can be added or subtracted. They can be added or subtracted at the summing point. That is how we found that. Then the takeoff point, we had the takeoff point is the point at which the output is taken for feedback purpose. And then we had a canonical form which consists of one forward path, one feedback path, and one summing point, and one takeoff point. And then we had the transfer function, which is the ratio of the output signal to the input signal in a control system, the ratio of the output signal to input signal of a control function. So in our next class, we are going to derive 3 ratios. We have the control ratio, the primary feedback ratio, and then error ratio.